where magnets are so powerful they could contain the sun's energy, maybe. Or think about an MRI machine, the world of iron-based superconductors, or FeSCs for short.
Hmm.
We've got this really comprehensive report here titled Engineering Supercurrents in Iron-Based Superconductors. It digs into advanced flux pinning and its impact on energy and magnet tech.
A hefty title, but important stuff.
Exactly. So our mission today is to unpack the most critical insights from this material. We want you to understand why these materials aren't just some scientific curiosity, but potentially a real game changer for energy, for science.
And they really were a surprise, weren't they?
That's what the report hints at. They apparently defied conventional wisdom.
That's absolutely right. I mean, superconductors themselves, they've been around for a century. But FSSDs, discovered back in 2008, they really caused a dramatic shift, especially in high-temperature superconductivity.
Okay, so what's so special about them?
Well, they offer this unique combination of properties, really advantageous for what we call high current, high field applications through powerful magnets, that kind of thing.
Right.
And an early aha moment, that the report brings out is how optimizing their current carrying ability.
Yeah.
It's not just physics. It's framed as a nanoscale mechanical engineering problem.
Nanoscale mechanical engineering. That's a really interesting way to put it. Okay, you mentioned 2008 was this dramatic shift. What actually happened then?
Right. So back in 2008, a research team led by Hideo Hosono in Japan made this truly astonishing discovery. They found a material containing iron.
Iron. But isn't iron magnetic?
Exactly. That was the shocker. For decades, iron's strong magnetism was, widely believed to be fundamentally antagonistic to superconductivity,
Yeah.
like the opposite of what you'd want.
So this discovery just flipped that idea on its head.
Completely. It directly challenged that long-held convention, really shook things up in the physics community.
Wow. Okay, so it wasn't just a one-off fluke then.
Oh, not at all. It kicked off this massive global research effort, and very quickly, researchers uncovered a whole family of related iron-based compounds that could superconduct.
A whole family? Like different types?
Yeah, different crystal structures, different compositions, things like the 1111 type, 1282 type, 11 type. And the key advancement came pretty fast. They found that by swapping out some elements, like replacing lanthanum with samarium, they could push the critical temperature, Ti.
That's the temperature where it becomes superconducting.
Right. They pushed Ti up to 55 Kelvin in one compound. Now, 55K might still sound cold, but it firmly placed FSS in the high-temperature superconductor category, way beyond what traditional theories predicted for conventional superconductors. It strongly hinted that something unconventional was going on with the underlying physics.
Okay, so high temperature is one thing, but you said they're good for high current, high field applications. What else makes them promising there?
Well, beyond just that high TC, there are two really critical properties. First, they have incredibly high upper critical fields. We call that HC2.
HC2, what does that mean practically?
Think of HC2 as the knockout punch for superconductivity. It's the maximum magnetic field a superconductor can handle before it just gives up and stops being superconducting.
Okay.
And FeSCs consistently show HT2 values exceeding 100 Tesla.
100 Tesla? That sounds like a lot. How does that compare?
It's huge. Conventional low-temperature superconductors, the ones used today in MRI machines like niobium titanium or niobium tin, they top out around, say, 11 to 25 Tesla.
Ah, okay. Big difference.
Massive. So FeCs can operate potentially in much, much stronger magnetic fields. That's crucial for next-gen applications.
So they're tough against strong magnetic fields. You said there was a second key advantage.
Yes, and this one is perhaps even more significant for making practical devices. It's their remarkably low electromagnetic anisotropy.
Anisotropy. Directional properties.
Exactly. Anisotropy basically measures how much the superconducting properties depend on direction. Think of wood grain easier to split along the grain, right?
Sure.
Well, other high-temperature superconductors, the cuprates, they're notoriously anisotropic. Their supercurrent flows much, much more easily in certain crystal directions than others.
And that causes problems.
Big problems for manufacturing wires. It means you have to get all the tiny crystal grains inside the wire lined up almost perfectly. That's incredibly difficult, complex, and expensive.
Right, yeah, gotcha.
But here's the fascinating part about FACs, especially the most promising types like the 122s and 11s. They have very low anisotropy. Sometimes the ratio is close to 1, meaning they're almost isotropic. The current flows nearly equally well in all directions.
Wow. Okay, so that sounds like a fundamental difference. What's the practical upshot of that for, like, manufacturing?
It's huge. It's a game changer, potentially. This near isotropy means the supercurrent flow is far less sensitive to how those individual grains in a wire are oriented. You don't need that perfect alignment.
So easier manufacturing.
Much easier. It enables simpler, more cost-effective methods, like the powder and tube process PIT, which is similar to how conventional superconductors are made. This could make FeSC wires significantly cheaper down the line. That's a major economic driver.
Okay, powder and tube. We might come back to that.
Definitely. And there's one more related point. Unlike cuprates, which start as insulators, most FeSC parent compounds are already metals or semimetals. This seems to help current flow between the grains, leading to better grain boundary properties, less of a roadblock for the current.
Okay, this is all sounding very promising, but here's where it gets really interesting and maybe a bit counterintuitive based on the report. Zero resistance sounds fantastic, right? But it's conditional.
It is.
Especially in high magnetic fields. These type 2 superconductors, like FeSCs, enter what's called a mixed state. Can you paint a picture for us? What's happening in this mixed state? What are these Abrikosov vortices?
Right, so imagine you apply a strong magnetic field. The material wants to stay superconducting, but the field has to go somewhere. So it penetrates the superconductor, but not uniformly. It goes through in these tiny, discrete, cylindrical filaments, like tiny magnetic straws poking through.
Okay.
Those are the Abrikosov vortices, or fluxons. Each one carries a precise amount of magnetic flux, one magnetic flux quantum it's called. And importantly, each vortex has a tiny core that's actually normal, not superconducting.
A normal core inside the superconductor, got it. So what's the problem with these vortices?
The problem arises when you try to pass a current through the superconductor while these vortices are present. The current exerts a force on the vortices. It's called the Lorentz force. Basically, it pushes them sideways.
Ah, like JAB from physics class.
Exactly that force, JAB. It pushes the vortices, trying to set them in motion.
And if they move, what happens then?
Well, if the vortices start moving, it's bad news for zero resistance.
Yeah.
Their motion actually generates an electric field inside the superconductor.
Electric field. But that means resistance.
Precisely. It leads to what's called flux flow resistance, and boom, your zero resistance state is gone. The material starts dissipating energy.
So all that promise of lossless current flow just vanishes if these vortices start moving around.
Correct. So the solution becomes clear. If you want to carry a large current without loss in a magnetic field, you must stop these vortices from moving. You have to pin them down.
Pin them down. Okay, how do you do that?
That's where the nanoscale mechanical engineering idea comes back. You intentionally introduce tiny defects or imperfections into the material structure. These act like obstacles or traps for the vortices.
Ah, so the defects pin the vortices in place.
Exactly.
Yeah.
And this defines the critical current density, JC. JC isn't some fundamental electronic property of the pure material. It's the maximum current density the material can handle before the Lorentz force pushing the vortices becomes strong enough to overcome the maximum pinning force holding them back.
So JC is basically set by how well you engineer these pinning defects. It's an extrinsic property.
You got it. It's all about the balance of forces. The Lorentz force trying to move the vortices versus the pinning force holding them still. JC equals FPB. More pinning means higher JC.
Okay, that makes sense. But the report mentions another challenge even with pinning, something called flux creep.
Right. Even when vortices are pinned, they aren't necessarily stuck forever.
Yeah.
Think of the pinning sites as little potential wells or hills the vortex has to overcome.
Okay.
Thermal energy, just the random jiggling of atoms due to temperature, can give a vortex enough of a nudge to hop over the pinning barrier and move a little bit.
Ah, so they sort of creep along slowly even when pinned?
Exactly. It's a slow, dissipative drift. Not as catastrophic as free flux flow, but it still introduces a tiny amount of resistance and limits performance, especially at higher temperatures or fields.
And this leads to the concept of the irreversibility line.
Yes. If you plot magnetic field versus temperature, there's a line on that diagram, the irreversibility line, or HIR2. Above this line, thermal energy is just too strong, the vortices hop around too easily, pinning becomes ineffective, and your useful JC basically drops to zero.
So a major goal for making practical superconducting wires is to push that irreversibility line as high as possible. Higher fields, higher temperatures.
Absolutely. You want the widest possible operating window where pinning actually works and JC stays high.
Okay, so we need pinning. How do engineers actually create these pinning sites? What's in the toolkit?
Well, what's fascinating here is how we actually engineer these microscopic structures. There's several mechanisms. The most dominant one is usually condensation energy pinning, or just core pinning.
Condensation?
Remember, the vortex has a normal core. Well, the superconducting state has lower energy than the normal state. That energy difference is the condensation energy. If you put a tiny, non-superconducting defect, like a nanoparticle, inside the material, it costs energy to make that volume superconducting.
Right.
So it's energetically favorable for the normal vortex core to just sit right on top of that already normal defect. It saves the system that condensation energy, creates a natural trap, a potential well for the vortex.
Clever. Like finding the path of least resistance or lowest energy in this case.
Exactly. Then there are more subtle effects called scattering-based pinning. If defects cause local variations in, say, how easily electrons move, the mean free path, or even tiny changes in the local critical temperature, EC, those variations can also create energy barriers that pin vortices.
So different ways to create these energy landscapes that trap the vortices, and the report mentioned that the shape of the defect matters too, like dimension.
Yes, the geometry is really important for how effective the pinning is. We can classify them. You have point defects, think zero-dimensional, tiny vacancies, maybe small clusters of atoms knocked out of place like you get from light particle irradiation.
Little dots.
Right. Then line defects, one-dimensional. Things like dislocations in the crystal structure, or, very effectively, those columnar tracks you can create with heavy ion irradiation. If you align these tracks with the magnetic field, they can be incredibly strong pinning sites.
Like tiny, sticky strings for the vortices.
Sort of, yeah.
Mm.
Then surface defects, two-dimensional. Grain boundaries between crystals or twin boundaries within a crystal.
Fleck traps.
And finally, volume defects, three-dimensional. These could be precipitates of another material or, very importantly, deliberately introduced nanoparticles.
Nanoparticles. Okay, you mentioned that as a pinning strategy. How successful has that been?
It's been one of the most successful approaches, especially in thin films initially. The report gives a great example. Adding nanoparticles of barium circonate BZO or BZO into films of a specific FeSC, the B122 type.
BZO and B122, what did they find?
Researchers figured out how to optimize the film growth process to create this nanocomposite structure. You get these tiny BZO nanoparticles, maybe 6 to 11 nanometers across, nicely dispersed within the superconductor.
And the result?
Dramatic improvement in JC. They reported values over 2 million amps per square centimeter, 2 mega amps per square centimeter at 4 Kelvin and 9 Tesla. That's seriously high performance, even beating conventional NBS at those conditions.
Wow. Any other benefits?
Yes. It also reduced the anisotropy of JC, made the current flow more uniform with field direction, and it significantly suppressed that flux creep we talked about, made the pinning much more robust.
That sounds fantastic. Is there a downside?
Well, there's always a trade-off, isn't there? You want lots of nanoparticles for strong pinning, but the nanoparticles themselves are not superconducting.
Ah, so they take up space that could otherwise carry current?
Exactly. Too many nanoparticles and you reduce the overall superconducting cross-section too much. So it's a balancing act, finding the optimal density and size of nanoparticles.
Right, optimizing the recipe. What about that irradiation method you mentioned? Creating defects with particles.
Yes, irradiation is another really powerful and highly controllable way to engineer pinning. You can choose the type of particle, the energy, the dose, to tailor the defects.
Like protons.
Proton irradiation is common. It tends to create mostly point defects, those 0D traps. And studies showed it could boost JC in certain FeSC crystals by up to 2.6 times at low temperatures.
Okay, boosting JC. But the report mentioned something really surprising with proton irradiation in some material.
Ah, yes, that was fascinating. In certain iron selenide telluride films, FeS-ERO, low energy proton irradiation, managed to simultaneously increase both channel Lucy and JC.
Wait, increase both how?
Yeah.
Usually introducing defects lowers TC, right?
That's the conventional wisdom, yeah. Defects needed for pinning usually mess up the superconductivity slightly, lowering TCA. But here, the theory is that the irradiation-induced strain in the crystal lattice actually locally optimized the structure for superconductivity, bumping TC up, while the defects themselves still acted as effective pinning centers for JC.
That's really cool. It shows these materials are quite tunable.
It really does. It highlights a unique aspect of SES. Sometimes you can improve multiple properties at once through careful defect engineering. It's not always a simple trade-off.
And what about heavier particles? Neutrons, heavy ions?
Heavier particles create more extensive damage. Neutron irradiation creates larger cascades of defects. Heavy ions, like gold or lead ions fired at high energy, can create those long, continuous columnar defects we mentioned earlier.
The 1D tracks.
Exactly. And those are extremely effective 1D pinning centers, especially when aligned with the field. In fact, heavy ion irradiation of certain SM1111 single crystals produced some of the highest JC values ever reported for any FeSC, up to 20 million amps per square centimeter at 5 Kelvin. Just huge numbers.
Incredible performance. So that shows what's possible within a single crystal or a thin film. But what about making practical long wires? That brings us back to the interfaces between the crystals, the grain boundaries, right?
Absolutely. For any polycrystalline wire, which is what you need for magnets and cables, how the current flows across the boundaries between individual crystal grains is critical. These boundaries can act as weak links, seriously limiting the overall current capacity.
And this was a huge problem for the first high-temperature superconductors, the cuprates.
A massive problem. Cuprate grain boundaries are notoriously bad for supercurrent transport. Even a small misalignment between grains can drastically reduce the current flow across the boundary. That's a key reason why making high-performance cuprate wires is so complex and expensive. You need exceptional grain alignment or texture.
Okay, so how do FeCs fare here? Is it the same weak link problem?
This is another area where FeCs really shine, particularly the iron pnictide family like the 122s.
Yeah.
They have a significantly less severe weak link problem compared to cuprates.
Less severe. How much less?
Well, studies on carefully made bicrystals, just two crystals joined at a controlled angle, show that in codoped Bayesian, the JC across the boundary stays quite high for misorientation angles up to around 9 degrees.
9 degrees compared to cuprates.
In YBCO cuprotes, the JC typically plummets after just 3 to 5 degrees of misorientation. And even at larger angles in the FeCs, the decrease in JC is much more gradual.
That sounds like a really important practical advantage. Why are their grain boundaries better?
It's thought to be linked directly back to that low electromagnetic anisotropy we discussed, and also the nature of their superconducting state. It's more like conventional swave pairing, less sensitive to orientation than the D-wave pairing in cuprates.
And the implication for manufacturing wires.
It means you don't necessarily need that incredibly precise, difficult, and expensive grain texturing that RBCO wires require. It opens the door for simpler manufacturing routes, like that powder-and-tube PIT method, to be viable for high performance.
Even if the grains are somewhat randomly oriented in the PIT wire, the current can still find paths across the boundaries relatively easily.
Exactly. Now, that's not to say grain boundaries are perfect in FeSCs. They can still be a limiting factor, especially if impurities form there during processing. So there's still work on improving grain connectivity.
How do they do that?
A couple of key strategies mentioned in the report. One is chemical modification. Adding small amounts of other elements, like tin, SNON, can act as a sort of lubricant or sintering aid during the heat treatment process. It helps the grains grow larger and bond better, and it can help prevent nasty current-blocking impurity phases like iron arsenide from forming right at the boundaries.
So, tweaking the chemistry, what else?
Process optimization is crucial too. Using techniques like hot isostatic pressing HIP, which applies high pressure and temperature simultaneously, can create much denser superconducting cores in the wires, squeezing out voids and improving grain contact. Also, carefully controlling the reaction temperature during wire fabrication is vital to avoid forming those unwanted secondary phases that can block current.
Okay, so through pinning within the grains and improving connections between the grains, you can really boost the performance of these wires.
That's the goal. It's engineering at multiple length scales.
So, with all this incredible nanoscale engineering, where can FeSCs make the biggest impact? Let's talk applications. High-field magnet technology seems like a prime target. Why are high-field magnets so important?
Oh, they're absolutely crucial for so many cutting-edge areas. You mentioned MRI machines earlier. Better magnets mean clearer images. Then there's NMR spectroscopy for drug discovery and material science. Particle accelerators like the LHC rely on powerful superconducting magnets to steer particle beams. And looking ahead, achieving controlled fusion energy will likely require magnets operating at fields beyond what's easily achievable today.
So, demanding applications. What are the key requirements for the superconducting wires used in these magnets?
You need wires that can carry a very high current density, JC, in those extremely strong magnetic fields, say 14 Tesla, 20 Tesla, or even higher. They also need high mechanical strength to withstand the enormous forces generated within the magnet. Plus, stability and reliable quench protection ways to manage the energy safely if a section suddenly stops superconducting are critical.
Okay, how do the engineered FeSC wires stack up against those requirements?
They look incredibly promising based on the progress reported. First, that high field JC performance. Engineered FeSC wires, especially the 122 type, are now showing exceptional JC, well over 100,000 amps per square centimeter at 4.2 Kelvin in fields way up to 24 Tesla, and still holding strong even at 30 Tesla.
Wow.
And critically, as we noted, their JC has a very weak dependence on the magnetic field once you get into those very high field regimes, unlike some other superconductors where JC drops off rapidly. That's a huge plus for magnet designers.
And that low anisotropy advantage must come into play significantly here, too.
Absolutely transformative. Think about REBCO tapes. They're fantastic performers, but highly anisotropic. This forces magnet designers into really complex winding schemes to make sure the magnetic field is always aligned favorably with the tape surface. It adds complexity and cost.
Right.
FeSCs, with their near isotropic JC, basically eliminate that constraint. You can wind magnets in simpler, more compact configurations, potentially more like how conventional low-temperature superconductor LTS magnets are wound. It could offer the performance of high-temperature superconductors, HTS, with the design flexibility closer to LTS.
That sounds like the best of both worlds in some ways. What about mechanical properties? Magnets generate huge forces.
That's another plus for the PIT process used for FSAs. You can use strong metallic sheath materials like stainless steel alloys around the superconducting filaments. This results in wires with excellent tensile strength and tolerance to bending strain, much better than brittle materials like MBSNJ or even the REBCO tapes on their flexible substrates.
So strong and flexible enough for winding.
Yes. And the PIT process naturally lends itself to making round, multi-filamentary wires. This is a big deal for applications like particle accelerators, where round wires are preferred. You can easily twist these filaments within the wire to reduce AC losses, and you can cable them together into standard formats like Rutherford cables, which are widely used in existing LTS magnet technology.
So you're getting HTS-level performance in a familiar LTS-friendly form factor. That's really appealing.
It really is. It lowers the barrier for integrating these advanced materials into next-generation magnets.
And this isn't just theoretical anymore, right? The report mentions actual demonstrations.
Definitely moving beyond just lab samples. Researchers have built and tested various test coils, like small pancake coils and racetrack coils made from SSC wires and tapes, and they've shown that the wires retain a high percentage of their JC, even after being wound into these coils, for instance. One report mentioned 87% retention at 10 Tesla for a 100-meter tape. That's crucial proof of manufacturability.
Any actual magnets built yet?
Yes. A major milestone was the construction of the first Tesla-class magnet wound entirely from FeLRS wire. It generated over 1 Tesla by itself, and significantly, it was successfully operated inside a 20 Tesla background magnet at a facility in Japan. That's a tangible proof of concept in a relevant high-field environment.
That's a big step. What about connecting wires together? That's important for large magnets.
Crucial. And there's been significant progress on superconducting joints between FeSC wires. They've achieved joints that can carry close to the full current of the wire itself, like 95% ratio, and have incredibly low resistance down the 10 ohm range. That's essential for persistent modal operation, where you charge up a magnet and have the current circulate indefinitely without a power supply, like in MRI and NMR systems.
Okay, so putting all this together, what does it mean? It sounds like FeSC magnet technology is really starting to mature.
It definitely seems to be moving rapidly from fundamental science towards engineering reality. The potential is clearly there.
Beyond magnets, what about other large-scale applications? The report touches on high-capacity power transmission.
Right. Superconducting cables are seen as a potential solution for several challenges in our electrical grid. Things like reducing congestion in urban areas, eliminating energy losses during transmission, especially for DC, making it easier to integrate large renewable energy sources like wind farms, and generally enhancing grid stability.
And high-temperature superconductors have an advantage there because of cooling.
Exactly. HTS materials, particularly REBCO, can operate using liquid nitrogen cooling, around 77 Kelvin. That's significantly cheaper and easier to handle than the liquid helium needed for conventional LTS cables, which operates near 4 Kelvin.
But FeSCs, their TC is lower, right? Around 30–40 K, so not suitable for liquid nitrogen?
That's correct. Their TC range puts them in an intermediate zone, too high for liquid helium to be efficient, too low for liquid nitrogen. So traditionally, they haven't been seen as prime candidates for 77K cables.
So are they out of the picture for power transmission?
Not necessarily. The report suggests a potential new pathway, a sort of dark horse scenario. It hinges on that potential for much lower wire cost via the PIT process. If FSC wire becomes significantly cheaper than REBCO tape, it might open up an economic window for cables operating at intermediate temperatures, say 20 to 30 Kelvin. You'd need more sophisticated cooling than liquid nitrogen, perhaps using modern cryocoolers that can efficiently reach those temperatures.
So the idea is that a much lower wire cost could potentially offset the higher cost and complexity of the cryogenic system compared to using more expensive RBCO at 77K.
Precisely. It's an interesting trade-off to consider for the future, but it's definitely a longer-term prospect. The primary hurdle right now for any superconducting cable technology, including FeSCs, is manufacturing very long lengths. We're talking kilometers with consistently high performance and acceptable cost. That's a major engineering challenge.
Right, scaling up production is always key. Okay, so we've seen the potential. How do FSCs really stack up against the competition? Let's do a quick comparative assessment.
Okay, benchmarking. Let's start with BSCCO, the first generation HTS wires. Compared to BSCC, AVGCs generally offer a significantly higher JC, especially in high magnetic fields. They're also mechanically much more robust. BSCCO is quite brittle and, importantly, far less anisotropic. So FeSCers look superior in most key aspects.
Okay, better than Gen 1. What about the main competitor, REBCO, the second generation HTS tapes? That seems like the critical comparison.
It is. This is where it gets nuanced. Let's look at performance. REBCO currently holds the edge at liquid nitrogen temperature, 77K, because of its higher TC. However, at liquid helium temperature, 4.2K, and in high magnetic fields, say above 15 Tesla, FECs are becoming highly competitive. And as we mentioned, their JC tends to decrease less sharply with increasing field compared to REBCO, those very high fields, maybe above 20, 25 Tesla. That can be an advantage for ultra-high field magnets.
Okay, so competitive performance at low temperature fields. What about anisotropy?
This is where FSCs have a decisive advantage. Their low anisotropy, gamma around 1 to 2, versus the very high anisotropy of REBCU tapes is a major differentiator, especially for magnet design, as we discussed. It simplifies things considerably.
Makes winding easier, more compact designs possible.
Exactly. And then there's the big one, fabrication and cost. This is where FECCs really aim to be disruptive. REBCO tape manufacturing involves complex multi-step vacuum deposition processes on sophisticated substrate templates. It's currently quite expensive. The report mentions figures around $100 to $200 per kilo amp meter.
Okay, pricey. And FESCs?
FESCs use that potentially much simpler powder and tube PIT process, which is similar to how mature LTS wires like NBTI and MBU AC-Eng are made. The cost targets being discussed for FESC wires are significantly lower. The report mentions a target of potentially less than $20 per gallon.
Wow, less than $20 versus $100, $200. It's a huge difference if they can achieve it.
It would be a massive difference. It could open up applications where REBCO is currently too expensive. So if you put it all together, the potential sweet spot for SEC seems to be in applications needing ultra-high field performance, say 20T magnets, where isotropy, mechanical robustness, and potentially lower cost are major drivers.
Let's quickly summarize those key comparative properties the report might have laid out in a table. TC.
Roughly. SEC around 38K for the 122 types, REBCO around 93K, BSCCO maybe 110K, and MBC around 18K.
Upper critical field, HC2 at 4.2K.
FEC and REBCO both potentially well over 100 Tesla. BSCCO maybe even higher, 150, 200T, but harder to use. MBC around 25, 28T.
Oh, okay. Current density, JC at 4.2K, and a moderate field like 10T.
This varies a lot with engineering, but represented values. SEC engineered wires over 2x10 ATC, REBCO maybe 6x10 or higher, BSCCO lower around 1x10, and MBC around 3x10 XCO. So all are high performers in 10T.
And anisotropy.
Key difference, SEC very low, gamma 1, 2. REBCO and BSC2 are high, and BSCO isotropic, gamma 1.
And finally, cost target per cam.
FSC targeting $20, RBCO maybe $100, $200 currently.
Yeah.
BSCCO 60, 80s, and mature NBS maybe $8, $10. So you can really see how FSCs slot in there. They're trying to bridge that gap, aiming for the high field performance realm of HTS, but with the manufacturing advantages and isotropic nature closer to LTS, and hopefully a cost point that makes them widely accessible.
That's a great summary. Okay, let's try to wrap up the key findings from this deep dive into engineering supercurrents in FSCs. What have we learned?
Well, we saw that FSCs possess this powerful combination of intrinsically high upper critical fields, HT2, and uniquely among HTS, very low electromagnetic anisotropy. This makes them fundamentally well-suited for high-field applications and potentially much simpler manufacturing into wires.
And their ability to actually carry high currents isn't intrinsic. It relies entirely on advanced flux pinning, which the report frames brilliantly as a nanoscale mechanical engineering problem.
It's about deliberately introducing and optimizing defects. Nanoparticles, irradiation damage, controlling grain boundaries to trap those pesky magnetic vortices and allow supercurrent to flow unimpeded. Multi-modal pinning using several types of defects together seems key to pushing performance limits.
And the progress is tangible. We're seeing potential for a paradigm shift in high-field magnet design, leveraging their isotropy and robustness, and maybe even a long-term prospect for power transmission if the cost targets can be met.
But it's important to keep the challenges in mind too. Significant hurdles remain before we see widespread commercial use. The biggest is probably scaling up production to make very long, uniform lengths of wire with consistent high performance reliably.
Right, the jump from lab samples to industrial production.
Definitely. And continuing to improve grain boundary transparency, minimizing any remaining weak link behavior, is still critical for PIT wires. Plus, drastically reducing the cost while maximizing the engineering current density, AEG, which accounts for the whole wire, including the non-superconducting parts, is paramount.
And safety developing robust quench protection for large magnets made from these new materials.
Absolutely essential. So future research will likely focus on even more sophisticated hierarchical pinning structures, maybe exploring new FSC compositions that are easier to process or have even better intrinsic properties, and really digging into the manufacturing science to achieve that scale and cost reduction.
So connecting this to the bigger picture, it feels like FASC technology is at a really pivotal point.
I think that's fair to say. A real inflection point. The fundamental scientific promise is undeniable, and the engineering demonstrations are becoming increasingly impressive and encouraging. The next few years will be crucial for seeing if that promise translates into widespread technological impact.
It's fascinating. As we've seen today, the future of harnessing these incredible supercurrents isn't just about discovering new materials anymore, is it? It's increasingly about ingenious nanoscale engineering, taking a material and fundamentally reshaping its properties by controlling its structure atom by atom, defect by defect.
It really is a shift in perspective.
So, here's a final thought for you, our listeners, to mull over. As you go about your day, maybe consider what other seemingly impossible scientific challenges might be cracked, not just by finding something entirely new, but by taking what we have and fundamentally re-engineering it at the atomic scale, one precisely placed defect at a time.
A powerful thought.
Something to think about until our next deep dive.